thank the organizers for having me here. Yeah, it's my first time speaking here, so I'm very excited. So today I'll talk about heterotic little string theories and inequivalent genus-one fibrations. So I've basically been thinking about this for the past, this sort of line of research for the past year and a half, along with Paul Constantine-Ohlman, who was a postdoc at Northeastern, and now he's at UCSB, and my advisor, Fabian Brule. So yeah, so today, I mean, I've sort of made this to be a more general talk about this line of like research. But hopefully, if you have time at the end, I can show you some of the results pertaining to this recent work, hopefully that we will have out by the end of the month. All right, so let me first try to motivate why we're looking at heterotic little strings and why we're looking at inequivalent genus-one fibrations. So the story between supersymmetric quantum field theories and geometry goes way back to the 90s, when people found that these seemingly different fields are related via string theory, or they're like non-perturbative generalizations, M&F theory. And so in particular, what people were able to show or see was that there's a precise correspondence between certain things on the geometry side and certain things on the physical or the quantum field theory side. So for example, certain masses of particles could be related to volumes of submanifolds, or like intersection of curves could be related to physical couplings, or I don't know, like singularities in the geometry could be related to gauge groups in your field theory. So there was this nice sort of thing that one could do, especially in the nicest cases where you had enough supersymmetry and so on. So the question then arises, why am I interested in this specific, what is this? You can think of LSTs as a specific kind of quantum field theory in 6 dimensions. And the reason we are interested in these theories is because these theories have an additional physical feature that sort of other quantum field theories don't have, which is known as T-duality. So I'll define T-duality more rigorously later, but for now, you can think of T-duality as taking 2 6-dimensional little string theories, you dimensionally reduce them onto a circle. So you look at the 5D theory, 5D effective theory. And then the point of T-duality is that these 2 different looking 6D theories are the same 5D theory. So then the question arises in this quantum field theory geometry correspondence. The question arises that what geometrical feature does this new feature of T-duality, this unique feature for LSTs, what does this correspond to in the geometry? And this is where the inequivalent fibrations come in. So I'll describe what I mean precisely by inequivalent fibrations later, but the point is that using this extra feature of T-duality, we are able to probe this extra feature in geometry, which is these inequivalent fibrations. And this will be the sort of the goal of this work. And also, please, if you have any questions, just interrupt me. Just know. Right. So in particular, in this realm, we'll focus on the following equivalents. So we'll focus on inequivalent genus-one fibrations for non-compact Calabi-Yau threefolds, whose base is birational to P1 times C. And the equivalence that we'll look at on the physical side will be the T-duality of a specific kind of little string theory, which is a heterotic little string theory. So again, just to take the point home, is that heterotic little string theories or little string theories are a specific kind of quantum field theory with this feature of T-duality.
Oh, quick question. Over the P1, are you getting compact K3s?
Yes, exactly. Yes.
Okay.
Precisely. And that K3 is important for us. If you know about the heterotic duality to F theory, you know that you need a K3. So this P1 gives us precisely that. Yeah, exactly. Good. So just to orient ourselves in the right way, I'll describe physically what we mean by little string theories a bit, and then I'll define them through the geometry. So physically, what a minimal 6D theory, so not heterotic little string theory yet, we will consider 60 supersymmetric quantum field gauge theories with 8 real supercharges, which gives us the following. Well, so when I say gauge theories, I'm just saying for now, I'm just associating some product of simple Lie algebras to this 60 theory. And throughout the talk, I won't be careful about the group, so we'll only talk about the algebras. And so the massless content of the field content of these theories is fixed by supersymmetry. And so you have 3 different supersymmetry representations: the vector, the hyper, and the tensor representation. And you have these various dynamical fields in the spectrum. So you have a vector boson, and then you have some fermions, you have some scalars, and so on, which transform under some representation of this gauge algebra that I've associated to this theory. And in particular, you can't just pick any values of the matter or the gauge algebras or the number of multiplets. These are constrained by some physical restrictions, which are given by anomaly cancellation and on the physics side. And in particular, what we're considering are minimal 60 LSTs, so LSTs with 8 supercharges. And so to define these, I have to first tell you another piece of data, which is this matrix eta ij, which is associated to the tensor multiplets that I introduced on the last slide. So this is sort of a pairing between these nt number of tensor multiplets. And in particular, some of the properties of this matrix are given here, where the elements are integer. It's an nt plus k by nt plus k matrix, where the dimension of the kernel of this matrix is k, which is important, because the little string theory is precisely the case where this k is equal to 1. So you have 1, 0 eigenvalue for this matrix, and that for you defines the minimal 60 little string theory. So via supersymmetry, what this tells you is that sort of all the fields that I just talked about, they're dynamical, right? But via supersymmetry, what you can show is that one linear combination of the phi's, which is a scalar field in these tensor multiplets, one linear combination of these is not dynamical anymore. And so this sets a dimensional parameter in your theory. And this is what people call the little string scale. And this is precisely because of the 0 eigenvalue that we have for this matrix. And furthermore,
I'm sorry, at this point, does this place any constraints on the geometry?
Yes, it will. And I will, when I get to the geometry, I'll show you what constraint this has precisely in the base. Yeah.
Got it, thanks.
Right, so yeah, right now I'm just telling you the physics like outlook, and then we'll map everything that I say here to geometry. Good. So the kernel of this matrix then is what I will call, like in the physics, it's called the little string charge. And again, this will have, of course, a mapping onto the geometry side, and I'm defining this here because I will use this later in this quantity later in formulas. So you don't really need to sort of care about the names per se, but just remember the notation. All right. So now I've defined for you in sort of a physics motivated way what a little string theory is. So now let me go on to their geometric construction via what I said earlier, this relation between quantum field theories and geometry. So one way to get supersymmetric 60 supersymmetric gauge theories is via F theory. So what is F theory? So F theory is a 12-dimensional theory. And the way we will get a 60 SUSY gauge theory, supersymmetric gauge theory, would be to take this F theory and reduce it onto a 6-dimensional, non-compact, elliptically fibered Calabi-Yau threefold, such that the effective theory then is 6-dimensional, which is what we need. And in particular, the Calabi-Yau threefolds, I know I probably don't have to motivate these much to this audience, but these are complex Kähler manifolds with a vanishing first Chern class, which leads to them admitting a Ritchie-Flat metric. And in particular, what's important for F theory is not just any Calabi-Yau threefold, it has to be elliptically fibered. So it has to have this vibration structure given by pi, where the fiber is a torus with a section. So a section is very important. So there's a divisor which intersects the fiber at the torus at exactly 1 point over each point of the base. And the base in particular for us has to be a non-compact Kähler surface, so that we can get a 60 supersymmetric, 60 gauge theory rather than a theory with gravity. So the base has to be non-compact such that we can decouple gravity from the physical theory. And so this is our setting. So in particular, let me sort of now map what I said earlier about the physical content to the geometric content. So this is sort of a nice, well, I wouldn't say nice, but this is a picture of my illustration of this threefold, which is elliptically fibered. So you have, of course, the non-compact B2 surface. Then you have certain compact curves in the base, which whose intersection matrix I've suggestively labeled as the eta matrix, which, as I'll show in a bit. Then you also have certain non-compact curves in the base. And furthermore, the most important thing, which is the most, I guess, the most beautiful thing about F theory, in my opinion, would be that you can encode the gauge algebras that I talked about earlier in these points that in these singularities that the torus develops over certain curves in the base. So you can have a vanishing discriminant, so one of the cycles of the torus can pinch or something. And then if you have this sort of singularity, there's a well-known classification for resolving these singularities, which is known as the Kodaira classification. And I guess the beauty came out when Kodaira found, and Kodaira and Neron, I think, they found that the way these when you resolve these by adding some P1s, the way these P1s and their intersection matrix looks like is precisely the intersection matrix of a ADE type affine ADE Cartan matrix. And so now you can already see I've sort of given you suggestions of what all this might look like from the physics side. And then indeed, I can now tell you the geometry and field theory correspondence. So these CI, these curves, correspond to the tensor multiplets, as I introduced earlier. The specific curves over which you have this discriminant vanishing, so where these singularities for the tori develop, you have the vector multiplets, i.e. the gauge algebras that I introduced. And then finally, when you have these curves intersecting, like these intersection points of the curves here, you get the matter or the hypermultiplets in the theory. Right, and also the volume of these curves sets for you the value of the scalar fields. And as was just asked just a while ago, the fact that you have a little string theory, it puts a constraint on the base that you have, and in particular, the constraint that you have is that there is a unique curve class in the base. So this, up to before this point, it was just a supersymmetric gauge theory. Now for an LST, you have, of course, the extra condition where this matrix eta has to have a zero eigenvalue. And that precisely translates to you having a unique curve class with zero self-intersection. And this is what, so now this is an LST, but this is not the heterotic LST that I'll talk about. So that there's extra conditions on that, and we'll get to that. Right. So now let me sort of define geometrically what I mean by T-duality. So to do this, I have to define for you first what MF theory duality is. So remember, I want to look at the 60 theory and I want to reduce it on a circle. So I've only given you like the geometrization of the 60 theory. I haven't told you anything about the theory that you get when you put it on a circle. Fortunately for us, there is a nice equivalence to another geometric construction for this F theory on a circle. So F theory on a circle is what I need, right? I need the 5D theory. it turns out it's equivalent to M theory, which is M theory is an 11-dimensional theory. It's equivalent to M theory on any genus one fibered Calabi-Yau threefold X prime with now possibly an N section. So before we had this, we had a section. So the F theory requires there to be a section and not an N section. But M theory has no such restriction. And so the point is now that you put M theory on any genus one fiber Calabi-Yau threefold with an N section, but it has to be such that the Jacobian of this X prime is precisely the elliptically fibered X that we use in F theory. So it's not just any X prime. Maybe I shouldn't have written any here, but it has to have its Jacobian needs to be X. And what I mean by this is that so these X primes are topologically distinct in general from their Jacobian. However, they have to share the same J function associated to the torus and have to have the same base. So that's how you define it. So what this sort of implies is that you can have different 5D theories, right? So you can have different X primes, right? As long as they have the same base and the same J function, you can have different X primes corresponding to the same X, right? Because the X can have, there can be many X primes such that they all share the same Jacobian. And this is the sort of the physical statement. Right. So now the question is, what do I mean when I like what does it mean in the physics when I say I pick an X prime, for example, for the 5D theory? What does that correspond to? So if I pick one X prime, what do I get in the 5D theory, and what happens if I pick another one? And the point is that if you choose X prime to be precisely the Jacobian, right? You just pick X prime to be the Jacobian, you get what I will define as an untwisted 5D supersymmetric quantum field theory. And if I pick X prime to be not the Jacobian, something else, some other Calabi-Yau with an N section possibly, then I get what I will define as a twisted 5D supersymmetric quantum field theory. And the reason I call it twisted is because now this fiber has an N section, and so what happens is that you now have certain monodromies that can fold your fiber, and folding the fiber, before we had ADE algebras so before the P1s intersected as the Cartan matrix of an ADE algebra, but now with this folding, I can get what are known as twisted affine algebras. And this is precisely why this is a twisted 5D quantum field theory. And what I mean by a twisted affine algebra, let me just illustrate this. So here you have the E6 Dinghet diagram. So this has a Z2 autoautomorphism. And so if you perform this autoautomorphism, you get what is known as this twisted affine algebra, E6-2. Yeah, so this Z2 is precisely, so if you want a Z2 folding, you would need a 2 section. And so if you want, say, a Z3 autoautomorphism twisted algebra, which is SO8, for example, you would need a 3 section in the fiber. So it's essentially to incorporating the genus one fibrations with N sections helps us realize these twisted algebras in the 5D theory. Good. Now let me state T-duality in terms of the geometry. So say I have a little string theory that I put on a circle, and the corresponding genus one fibration is given here with a pi, which is defines the fibration and the base and then the fiber. And there's another little string theory on a circle which corresponds to a genus-one fibration of the same Calabi-Yau, but it's an inequivalent fibration within the same Calabi-Yau, given by this pi prime here. Then we say that the two LSTs are T-dual, and in particular, they correspond to inequivalent fibrations within the same Calabi-Yau threefold X. This is the definition of T-duality from a geometric point of view. So inequivalent fibrations with the same Calabi-Yau.
So let me just ask here. So it's enough to change the elliptic fibrations on the compact K3, on the K3, right? That's okay?
Exactly. Yes, exactly. Precisely.
Okay.
Right. Because but right now I'm sort of making a more general statement about just LSTs, not the heterotic ones with the P1 times C base. So yeah, but when we
okay. right now it's just a non-compact surface base.
Exactly, with the zero curve, zero self. Exactly.
Got it.
Right. Later we'll see the K3. Yes. But yes, you're right. It's enough to change look at the different vibrations of the K3.
All right. Thank you.
Good. So good. So these are the same 5D theories, but with different 60 uplifts. This is the definition of T-duality, right? So that's what I how to define. So two different looking 60 theories give you the same 5D theory. But why is this the case? And the answer is MF duality. And now I'll say something in physics motivated, but you can of course question me on this. So the point is that in F theory, the fiber is not a physical. Moving in the Kähler moduli space of the fiber is not something you can do in the physics. Whereas in M theory, the fiber itself is physical. So moving in you can sort of move in the Kähler moduli space from one vibration to the other. You can go from say this vibration to the other, and that just means that your theory is the same. Your 5D theory is the same theory, but it has different 60 uplifts because in 60 or in F theory, you don't have the freedom to move in the moduli space of the fiber. So you can't really go between these two vibrations. Because F theory is really just a tool that we use. It's not a physical theory. And I mean, one way you can think about it is because in 12 dimensions, we don't have a supergravity theory that it could reduce to at lower energies. So yeah, the point is that the reason you have the same 5D theories is because you can move from this vibration to this one in M theory. All right. So now one question that you can ask from the physics side is what are the invariants that sort of must match across any candidate dual theories, right? That's a physical. If I can match some invariants, I can at least say that there's a chance that these theories are dual. And then this obviously translates to the math question, which is what are geometric invariants of inequivalent genus-one fibrations of the same Calabi-Yau? And this is precisely the correspondence that I will talk about now. All right, so let me sort of say what these T-duality invariants are in terms of both the field theory and the geometry. So the first invariant is the Coulomb branch, is the dimension of the Coulomb branch of the 5D theory, or you can think of this also as the dimension of the Kähler moduli space of the 5D theory. On the field theory side, this is the total rank of the gauge algebra. Whereas on the geometry side, this is just the Hodge number H11 of the Calabi-Yau minus 1. When I say I'm being sloppy here slightly because our geometry is non-compact. So when I say H11, I just mean the compact Kähler moduli. And then you have this other quantity, which is on the field theory side is what's known as the rank of the flavor symmetry. And on the geometry side, this is known as these are the number of non-compact divisors that you have in your geometry. And so you can sort of, I guess you could, these first two invariants are something you might find that are kind of, this is kind of trivial, that it shouldn't matter what fibration you pick. This is always the same. The number of non-compact divisors you may also think is sort of a trivial invariant. But this third one, this is completely, well, it was a surprise to me when I saw it, at least. These invariants are physically motivated in the sense that these kappa R's and kappa P's are mixed anomalies of the physical theory, and so we expect these to match in any physical duality. But from the geometry side, you can see that this is something that is like with the little, this is related to the matrix eta, which is the intersection of the base curves, and it's null vector here. And then it's really then multiplied by what's known as the dual Coxeter number of an affine Lie algebra. This is essentially, from the geometry side, you can think of this as the sum of the multiplicities of the different P1s that resolve the fiber over a specific simple Lie algebra. And then this is a purely base quantity, right? This is only base dependent because you have this eta, which is just the diagonals of the intersection matrix, and this is the null vector. So these two also turn out to be invariant, and which, at least for me, was not something that was intuitive from the geometry perspective. And so, in particular, the goal of our most recent work was to show that when these algebras are allowed to be twisted algebras, i.e., you are allowed to have genus-one fibrations rather than just the elliptic ones, do these invariants continue to match for dual theories? And in particular, what is a nice sort of fact is that the dual Coxeter number for a simple Lie algebra G, affine Lie algebra G, and its twisted version is actually the same, so it doesn't change into twisting. And then you can also see that the kinds of twists that we're talking about also don't change, like the folding of the fibers does not change anything in the base. So this would also be trivially invariant. So twisting does not actually change these quantities. It does change these, as we'll see. All right, so now that I've sort of defined for you what T-duality is, we can now sort of talk about what heterotic little string theories in particular are. So, the 60 heterotic little string theories are they sort of descend from the two known supersymmetric heterotic strings. You don't need to know what those are, but I'll just state what they. So the one kind is known as the E8 times E8 little string, and the other kind is known as the SO32 little string theory. These are the sort of the gauge bundles for these two theories. But from this point on, I'll just call them A and B. And so our goal is to sort of look at the T-dualities of these guys here. In particular, you can label these theories by a three-tuple. So this number M here, this affine Lie algebra here G, and then some coefficient alpha, which and these sort of things, these quantities are specific in the sense that M has to be a positive integer, and then G1 is some ADE type affine Lie algebra. And in particular, what's interesting about these two theories and what relates them is the fact that M and G encode the base and the compact fiber data for LSTA, whereas it's reversed for LSTB. So in that case, G actually encodes even though it's sort of maybe unintuitive, G encodes the base data, whereas M encodes the fiber data. And this is what sort of makes them T-dual, is this, in physics, what's known as this fiber-based duality. And the alpha, I won't really talk too much about alpha, but it basically encodes all the non-compact data for your geometry. So just to reiterate, the M and the G encode base and compact fiber data for A and B, but their roles are reversed for B compared to A. And the alpha encodes just non-compact data for the geometry.
So will you tell us the geometrical interpretation in terms of the fiber K3s?
Yeah, it's the next slide.
Okay, great.
Yeah. So good. So the geometry of the 60 LST is, so for heterotic LST in particular, B2 has to be birational to P1 times C, which, as we've been waiting for now, implies a K3 fibration in your geometry. And from the physics point of view, this K3 fibration sort of had to be there because it's known for heterotic string theory to have a dual in F theory, you need a K3 fibration. And then, as again we were waiting for, is that this fibration structure, this elliptic fiber, is actually a fibration of the K3 itself. So it is sufficient to just look at the vibrations of the K3, and you can just look at the inequivalent vibrations of the K3, and then you would have your inequivalent, you would have your T-dual theories. And in particular, alpha, which is the non-compact divisors, are encoded in the K3. So this is precisely what this is sort of clear here, that the non-compact divisor, so the K3 lives on the non-compact curves in the base. So now we can sort of put these theories on a circle, which is what we want. So remember, the choice of twisting corresponds to a choice of a genus-one Calabi-Yau with the same J function as your F3 Calabi-Yau X. And so and then further remember that the twist, what I call the twist, or what you may think of as the choice of the genus-one, acts on the torus fiber. So if I take this 6D LST given here, either A type or B type, and I want to look at the 5D theory, so I pick some genus-one Calabi-Yau with the same J function as X, then the way it acts on A should obviously just act on. So let's forget the non-compact bit for now. I'll explain this separately, but look at the first two entries. So for A, I told you that the fiber data is encoded in this ADE algebra. So the twist has to act on this, which is now given by Gn, whereas in the LST of type B, the fiber data is actually encoded in M, and so M can be modified under the twist, and it can be now M prime, for example. Alphas, on the other hand, can be modified for both of them under this twist. In particular, because, like I said, alpha is encoded in the K3, and the K3 itself has the fiber, encodes the fiber itself, and so any twist would modify both of these. But again, alpha I won't focus on that much. It'll basically be these two, and I'll comment on this at the end as to why I think that it's sufficient to focus on the first two. Right. So now in particular, let me I'll summarize the how we try to match the invariants. Like, even before I go to geometry, I'll just show you the strategy we use to sort of match the invariants on any candidate T-dual theories, for any candidate T-dual theories. So again, consider some heterotic little string theory, untwisted. So just from the F theory, given here, the two types are given here, A and B. One can show that the Coulomb branch dimension, which is one of the invariants, can be written as this guy here. So it goes in particular linearly in M. And these coefficients depend, this first coefficient here depends on your gauge algebra, and the second constant shift depends on the alpha. Similar thing for kappa R, but just that the functions are different.
Oh, can I ask? I mean, you based on my questions, you'll probably get to this on the next slide. But I guess what I'm wondering is, what conditions do you have on the Picard lattice, the Néron-Severi rank of the K3? Are you assuming that it's elliptically fibrous section of rank 2? So nothing special happening, or can it go much higher?
Yeah, so it can go so good. So the Picard lattice we don't put any restrictions on. So it can go up to, so you can go up to the extremal rank. So it can be an extremal K3 as well.
Well, if it's extremal, you'll be isotrivial in your C direction, but that's okay, I guess.
Yeah, so with the extremal, so good. So yeah, the extremal is a special case. So, but yeah, in general, we don't have any restrictions on the K3 because that really just gives us, some different duals. So if I pick a K3 with some Picard rank, that would give me some class of T-duals, and I pick another Picard rank, so some lesser in terms of the physics, that would be some lesser flavor symmetry, or that would give me a different class of duals.
So where do I see the Picard rank entering, say, into the Coulomb branch calculation? Is it showing up there?
No, not in the well, okay, good. Yeah, it does. It shows up in these constant pieces here.
Good, that's what I thought. Okay.
Yeah, exactly. Yeah, as a function of alpha. Yeah, exactly. So if I change alpha, I change what the Picard rank, and then I change this constant piece.
Great.
Yeah, exactly. Good. Yeah. Right. So good. And the kappa p, the third invariant is actually always just 2 for heterotic LSTs, which is also very interesting. But the point is, by the end of this talk, hopefully I'll convince you a bit that this can also change. But for now, let's just focus on the other 2 invariants. So if I twist A, so if I choose a genus-one fiber, you get so maybe let me take it back for a bit. I told you earlier that kappa R actually doesn't change under twisting. So this thing would remain the same, whatever genus-one geometry I pick. So the only thing that can change is the Coulomb branch, and also the flavor symmetry. But let me ignore that for now. I'll comment on that a bit later. So right now we're just looking at how the Coulomb branch changes when you twist, or when you choose a genus-one fiber. So here you can see clearly that this function C2 can depend on if it's twisted or not, and the same thing with this C1. So this would essentially correspond to you picking a genus-one fiber for the K3. And similarly, if you twist B, then now the action is, as I said, the fiber data for B is encoded in M. So now this thing remains the same. M can change. And C1, of course, can also change. And so what we want to do, and what has experiences showed us, is that we should be able to find, for a fixed C1, C2, R1, R2, we should be able to find duals for all M. So M sort of should be like a parameter that you can vary however you want, but you should be able to find duals in families of M. And so using this, just what again our experience shows us, which is why I also didn't talk about the alphas, was that we only really need to always match the leading M-dependent piece. And it's always, if I can match the leading M-dependent piece, it's always possible to match the rest of the invariant data. So it's always possible to choose a K3 or a Picard and an associated Picard rank, such that you can match the rest of the invariant data, and you can match the C1, the constant pieces. And again, I'll comment on this a bit at the end, because we sort of have kind of evidence that maybe the invariants that I showed you are not all independent. and it could be that sort of the alphas are dependent on this other data, and so you can sort of get rid of one of the invariants. But we're not sure about this yet. We have some evidence, but yeah. So, right. So this C2 and R2, these coefficients are known for the untwisted theory. So where you just pick the elliptically fibered Calabi-Yau. But you can then also sort of determine these coefficients. Well, what we did, at least, we first determined these via field theory. So we used the physics to determine what these coefficients would be for any twisted theory. And then sort of the strategy to find dual theories that we used was to just match the linear M-dependent terms, then match the constant terms, and then try to find the geometry that sort of realizes our field theory predictions via inequivalent fibrations within the same Calabi-Yau. And yeah, so now with this sort of setup, let me sort of give you some examples of how this is realized. So the first sort of canonical example is the famous E8 SO32 T-duality. So this is predicted both from like string theory and field theory arguments, and was shown via geometry a while ago by Aspinwall-Morrison, that you have this sort of duality between an A-type theory and this B-type theory, where these with the sort of the way I defined these three tuples was keeping this in mind, essentially. That's why it looks the same, but these A and B here. So this is the canonical duality that was predicted from field theory and was shown in geometry a while ago. But now recently, about I think a couple of years ago now, people found, these authors here found another inequivalent fibration within their geometric constructions that predicted another T-dual of type B, where now the base is actually, instead of just being a base of type G1, it was a base that was sort of folded by a symmetry or an automorphism of this G1. So this was not, there was no field theory evidence or physics evidence for this kind of theory to exist, but they found this inequivalent vibration within the Calabi-Yau, and it satisfied everything that you needed from a field theory dual, but it wasn't known in the physics, and still we don't really understand its origins that deeply, but there's more, we know more about this dual now. And so this now you can extend this duality chain by adding this extra folded B-type dual. Right. So yeah, essentially they found another sort of K3 fibration within the sorry, they found another elliptic fibration within the K3, and then they were able to form a full theory out of it. Now, what we did in this paper, so right now I've only talked about untwisted stuff, right? So what we did in this paper was sort of try to find duality chains where now you have twisted T-duals appearing as well. So now you have fibers with end sections appearing. And so what we did was, using what I showed you earlier in terms of the M data matching, we predicted that there should be a dual for between two A-type theories here, where you can see the number of this M is n times the M here, and the algebra itself is twisted by this automorphism of the algebra. And in particular, the G's that satisfy this are given here. So these are the twisted affine algebras, and these are the regular affine algebras. And we found that there should be a duality between these if M is related in this way on both sides. And in particular, this, now we went the other way, right? We used field theory to predict that there should be another genus-one fibration that realizes this duality. And indeed, we constructed these fibrations using toric methods for all of these algebras here. Well, for SU, we did SU4, but we didn't do the others because torically it's not possible to get these SU2 and two-type algebras, but for all the others, we have explicit geometric constructions that precisely realizes this duality. This table was sort of very surprising to us because, I mean, there should be some, I think, there should be some group theory argument for why these algebras should be related in this way, but we don't know this currently, and there is some evidence for these two guys, which I can talk about later, these last two, but we don't know why these algebras would be related in this way. But of course, we have the geometries, we have the physical arguments, so everything works out. Yeah, we predicted this duality. We have other sort of duality chains, including other twisted theories as well in the paper, but these were the cleanest geometric examples that we had, and so that's why I'm sort of presenting those here. Finally, let me sort of at the end, let me sort of talk about some work that some hope for these other theories that we were able to construct. So using sort of just field theory, sorry, question? Okay. Using some field theory arguments, we were able to show that sort of you are also allowed to do twists that fold the base of the fibration. So not just, so before if you recall, I was folding I was folding the fibers due to the monodromies, due to the end section. But field theory also tells you that you should be able to fold the base. When you do that, you can change this eta matrix. And in particular, what you get are these twisted two-group structure constants. And so these are the ones that now these can be modified too. Because remember, when you fold the fiber, these weren't modified. But if you do this sort of physics way of just taking this base, folding it, and so on, you can actually construct T-dual theories with kappa p equals 1, which I actually told you is not possible because I told you that you only had kappa p equals 2. But it turns out that if you allow folding of the base, you can realize these new families of T-duals for which we actually do not have geometric constructions. And so this is sort of the future goal now, is to be able to show that this prediction from field theory you can actually realize as an inequivalent fibration, as inequivalent genus-one fibrations. And so that would be, of course, great if we can do this, but so far we don't know. So yeah, that would be nice to like sort of keep this field theory geometry correspondence going. Right, so now let me sort of just I think I'm in time, so let me just end with some outlook about some future questions. So of course, one thing that would be nice to do is like from the math perspective, of course, it's interesting to find inequivalent fibrations of other base types and not just P1 times C. So it would be interesting to see if this question also can be mapped to some physics question, just like these heterotic LSTs were mapped to P1 times C base types. The other thing that would be interesting would be to see if this has implications like for inequivalent fibrations of Calabi-Yaus with compact bases. So in our constructions, the way we construct these Calabi-Yaus is actually taking a compact Calabi-Yau and then taking its decompactification limit. And it would be in particular interesting to look at this in the case of compact bases from the physics perspective, because now when you have compact bases, you have the physical theory now is not a supersymmetric gauge theory, it's a supergravity theory. And so it would be interesting to see if sort of all the fibrations of the non-compact case go into the fibrations of the compact case. And so that would tell you a statement about the relation between T-dualities of supergravity theories and T-dualities of LS little string theories. And then finally, this is sort of the question that we are now looking into, if all the T-duality invariants that I showed you are really independent. In particular, because we can sort of always find a K3 or sort of a fibration in the K3 that gives us the right matching data, it seems to me that maybe it's not all of them are independent, and sort of you can one of them is fixed by all the others. And we have a certain, like for certain examples, we have we have we actually have the analytic relation between these, but it doesn't hold for all the examples, so we don't really know this yet. And then finally, this is sort of more, I guess, speculative. What are the implications for the Weil-Chatelet group of these genus-one fibered Calabi-Yaus? So I didn't define this earlier, mostly because it's hard to define. But there's a group that you can group and an action that you can associate to these genus-one Calabi-Yaus that share the same J function and the same base. And so we would like to see if the field theory can tell us something about this group itself. And yeah, and there's many more questions, but that's what I would like to sort of highlight here. So yeah, thank you for your time. And
yeah, thank you, Hamza. So any question for the speaker?
Oh,
Okay,
Hamza,
so,
sorry, I've got one. Can I ask? Yeah. So a quick question. So how does mirror symmetry play with this story?
Right. So you're saying what happens if I look at the mirror Calabi-Yau?
Yeah. I mean, there's yeah. I mean, there's that, and there's mirroring the fiber K3s and.
Yeah, that's a good question. I haven't really thought about the mirror, but I
mean, from a physics standpoint, I mean, setting aside the slogan T-duality is mirror symmetry, you know, setting that aside, do you have a direct connection to a 2A or 2B theory?
Good. So yeah. So first of all, there's no T-duality between a heterotic little string theory and the type 2 theories. So I guess maybe in the context, so I didn't talk about them here, but there are type 2 little string theories as well. So in that context, actually, it is shown that actually that's a good point. Yeah. So in that context, actually, it's shown that the type 2A little string theory is T-dual to the type 2B little string theory. So their mirror symmetry is equal to T-duality in some sense. But what's interesting is that in that case, they also realize them as inequivalent fibrations of the same Calabi-Yau. So it can't be the dual Calabi-Yau then, right? Because it's the same Calabi-Yau, but you're just looking at different fibrations of it. So in that case, I guess, yeah, I'm not sure, because that would seem to say that mirror symmetry is not T-duality, right? Because it's the Calabi-Yau, you're not going to the mirror Calabi-Yau. Yeah, I mean, that's a good question. I'm sorry, I don't have much more to say on that, but yeah.
Yeah, I mean, maybe we should talk to Fabian about it. But
Yeah.
I think there's some interesting questions to be pursued here.
Definitely.
Just in terms of how mirror symmetry plays with this whole story.
Right.
Yeah.
That's a good point, because in the type 2 case, it seems to me that sort of that the T-duality, the way people have done that, like between type 2A and type 2B, like when I say type 2A, type 2B, any relation that comes to my mind, and probably your mind too, is mirror symmetry. But in the case of LSTs, people have the relation between them is inequivalent fibrations, the same Calabi-Yau. So that is actually kind of like, I guess, a contradiction, but maybe in the because again, these are non-compact. So maybe I don't know what the status of mirror symmetry in the non-compact case is, but
well, it's well studied for non-compact Calabi-Yau threefolds, especially the ones that are toric total spaces of the canonical bundle, say, over toric varieties. But I think it's the kind of thing where one has to sit down and throw some stuff at the board and see what might be true.
I agree.
But the nice thing is you all seem to have a lot of very explicit examples, so it seems checkable. We can sort of
we have explicit toric constructions, and this toric stuff, everything is like clean, and you can just see it. yeah, but that's a good question. Yeah, we should definitely talk with Fabian about this.
Okay, great. Sounds good. Thank you.
Okay, so if no question, let's thank the speaker and
Thank you.
okay, thanks and bye.
Take care.